Hello everyone. Today we'll go over our analysis of a double pipe heat exchanger. Our class is MNG4330 Process Control. Our group consists of myself, Omar Bandello, of Carlos Chick, Brittany Fink, Deval Patel, and Roberto Sainz. A quick overview of our presentation includes our introduction and background information, some of our motivations and objectives, our methodology, the discussion of our results, a conclusion, and some of the references used for this presentation. Looking at a quick background of heat exchangers, the main purpose of these is to transfer heat between fluids. The main types that are used include shell and tube as well as double pipe. Different variables that can affect the effectiveness of heat exchangers include the temperature of inlet fluids, the flow rates of these fluids, as well as the controller used. Heat exchangers are used in many different industries, ranging from petroleum to nuclear. And in terms of industries, the goal of heat exchangers is to achieve a desired temperature of an upper fluid for later use. Our project will look deeper into the use of double pipe heat exchangers. As seen in figure 2, the layout consists of two concentric pipes in which fluids will travel through both pipes. It is most common that the warm fluid travels to the inner pipe, either in parallel flow or counterflow to the colder. Because of this layout, the heat transfer occurs from the inner to outer tube, and some of the variables that can affect the effectiveness of these include the length of the pipes, the material of the pipes, and the thickness of the inner tube walls. Controls are important tools to help an outlet fluid achieve a desired output temperature. This is done by analyzing the current output temperature and adjusting the inputs in order to get closer to the desired output temperature. Different types of controls are considered depending on the industry and task, featuring from the PID, the feed-forward, and the cascade. For this project, we'll focus on the PID as well as the PMPI to analyze and compare the effectiveness of each type of controller.
Motivation and objective. Project objective: to develop a control system for heat exchangers so that the desired outlet temperature can be achieved by controlling the flow rate. Motivation: an understanding and prospect of improving the design, modeling, and control of double pipe heat exchanger in MATLAB Simulink at different conditions. Here we have a model created in SolidWorks. The model on the left is a double pipe heat exchanger, which is a control volume. The model on the right shows the overall system of the double pipe heat exchanger. The arrows show the parallel flow, and red is where the hot fluid flows, and the objects in blue show where the cooling fluid flows. The two objects in the back are our boilers with an integrated control system. Methodology: a model of double pipe heat exchanger was created using SolidWorks as shown in the previous slide. Mass and energy balance methods are used to create the mathematical model, which will be presented later in the presentation. MATLAB and Simulink will be the tools to simulate the heat exchanger and its controller. Main objective is to test the effectiveness of P, PI, and PID controllers to control the output temperature of fluid and compare the effectiveness of each, and use what we have learned in process controls to properly tune a PI and PID and P in order to see which controller is best for our system. Next, we will have results and discussion.
Here we have our assumptions, our negligible potential kinetic energy, no phase change of the fluid, no fouling in the system, flow along streamline, standard ATM, parallel flow, fully developed flow, insulated heat exchanger, steady state flow, incompressible fluid, well mixed tanks and heat exchanger, no external work, hot fluid flows on inner pipe and cold fluid flows in the annulus section. Here we have our givens. We have separated them out from the hot side at the top and the cold side down at the bottom, and we can begin our problem. Our properties from the tables. As you can see, we separated from the pipe side again, hot side, and then the annulus, the cold side. We also have our water and the different rates that they are at. different specific heat values. This will help us formulate the next steps of the problem. Here we see our mass balance equation, and we can see that no accumulation of the mass in the control volume. It is a steady state mass flow. We can see that the flow in is equal to the flow out.
Now that we have our Nusselt's number, we can go back to calculate the convective heat transfer coefficient. And with our convective heat transfer coefficients for both the annulus and the pipe side, we can find our total thermal resistance.
So after solving for the total thermal resistance, we can now determine the overall heat transfer coefficient by using our given dimensions and the area of the surface of the pipe and area of the surface of the annulus, as the overall heat transfer coefficient is reciprocal of the total thermal resistance. Now that we have our overall heat transfer coefficient, we can solve for the rate of heat transfer. Now the rate of heat transfer is calculated by using the overall heat transfer coefficient times the log mean temperature difference value of a parallel flow. And we have gotten a value of 27.52 Kelvin. And the larger the log mean temperature value is, the more heat is being transferred. And that you can see from the rate of heat transfer, which is 5.384 watts. So after solving and calculating for all our variables and parameters, we can now come to the conclusion of these two following simplified energy balance equations, one for the pipe and one for the annulus. Now from using these equations of the mass and energy balances, we can now start developing our model by incorporating Simulink and MATLAB respectively. Thank you so much for your time.